All right, this is not quite a bell curve, it seems. Okay, so most people, it seems like, have got completed graph vertex class. I guess I should have added an option that says did not complete my graph or vertex class. Hopefully everyone was able to at least complete number one. Maybe add a comment if you weren't able to complete the graph vertex class. It should be anonymous in case you're shy. Okay, but it also seems like not that many people were able to get to the searches, or at least 21% of you were able to, but the other 79% were not only. Okay, well, we'll go through the solution for the graph class. And then we'll also spend some more time going through BFT and then DFT also. What did you find difficult about it? You can drop more comments in. Like, what did you just run out of time, or did you feel like it was too difficult, or the instructions weren't clear? We didn't cover creating a graph class, but we covered the components. So it was left to it as an exercise for you to create the graph class. We'll go over that today, but if we go over it before you have a chance to implement it, I think that the learning is not as complete. So we went over what a graph was. We went over two different representations, including which were the adjacency list and adjacency matrix. And then we went over the operations that were needed. So that should have been enough pieces for you to figure it out. But maybe we could have gone over some more. I'm not sure what else we could have added that didn't reveal the answers. Okay, that's fair. That's fair. Well, we have one more day. We're going to spend one more day, and we're going to go through a lot of traversals today. So I'm going to walk through BFT, breadth first traversal, and DFT, which is depth first traversal. And then for your homework, you're gonna have. I guess I can also go through DFT with recursion. That's traversals, and then for homework, you're going to be working on searches, which are similar. They use the same basic algorithm, but there's some trickiness to them. Searches meaning you start from a node, and you have a destination node, and you search to find that node, and if you find it, you return the path to that node. That's more often what DFT and BFTs are used for, is to search for something and then find the shortest path. All right. You also may have noticed that the graph, this graph repo has been updated. So check it out. Maybe merge if you can recopy this file, the README file, or you can I don't know, refork or reclone the repo. But anyway, just make sure that you have this updated version. I'm going to be continuing to update days 3 and 4. I'm going to add some stretch goals to this. But basically the changes are for days 1 and 2. We're just focusing only on searches and traversals. So we're on day 2 of this. So we went over what the graph class is, and then we went over breadth first traversal in pseudocode a little bit yesterday. And now we're going to keep going with that and get through all of these different kinds of searches today. All right, so by the end of today, by the end of lecture, you should be able to implement breadth first, depth first, searches, and traversals. And for depth first, you should be able to do this using recursion or using a stack. All right, that's our goals for today. Less pseudocode and more actual coding. So I'm going to write it in pseudocode, and more as far as actual coding, that's left to you as an exercise for your homework. We're going to go over this. We'll go over this on Wednesday, the code solutions. But but we want you to do coding. You know, how much learning do you get if we just give you all of the answers, right? I don't think you get that much out of it. Part of computer science is being able to figure these things out for yourself as well. There's a lot less handholding, intentionally so, than in your main tracks, because what we really try to push here is critical thinking, and in order to do that, we throw really difficult problems at you. You may have heard this in algorithms, but the way that you should think of algorithms is first you think of, how am I going to do this? Like you think of it like the idea of what the process is going to be in words, and then you can even write it out into a sentence. And that's what I'm going to be going with you today. Like how do you describe breadth first search in a sentence? And then from the sentences, you can change your sentences into pseudocode, and then you can change your pseudocode into actual code. And the nice thing about Python, and one of the reasons we use it for computer science, is that Python syntax is very, very close to the English language. So pseudocode is actually very, very, very close to your actual Python code. So if I walk you through at least the sentence form, you should be able to generate the pseudocode from that, and then you should be able to write actual Python code from that. That's fair. That's totally fair. And we understand that you've only been doing Python for 2 weeks now. But this is also part of the learning process. A lot of times when you start a new job, you'll be learning new languages as you start the job. You know, this is a pretty common occurrence. Like I've started many jobs where I'm coding in a language that I didn't previously know. And you get maybe a week to ramp up, you know, you get a week to study, and then they want you to start contributing work. But if you have trouble in Python, David, are you iOS or are you full stack web? iOS, okay. So if you're used to Swift or Objective-C, that is a little bit further of a leap than going from JavaScript to Python, but it's still fairly similar. Like the concepts are all the same in every language. If you need help with Python, definitely ask your PM, or you can ask me also, or any of the other instructors, and we can help you get through if there's any specific problems that you're having. This is also why we want you to think of it in sentence form, because the sentences, right, that doesn't matter what code it is. Like if you can write out the sentences and write out the pseudocode, everyone should be able to get to that point. And then, all right, converting your pseudocode into Python. If you can get that far, like definitely talk to your PM and say, like, this is my pseudocode. I think it's right. I'm having some trouble with the Python, for whatever the reason is. And then it should be pretty easy to help you through that part. Having code that sounds or looks good but doesn't build is frustrating. Yeah, absolutely. That's just the reality of being a coder, right? 50% of your time is maybe coding, and 50% of your time will be bug fixing. And the more experience you get, you can shrink the time for bug fixing, but that's definitely a huge part of software engineering. But that's why we're here. You're here to learn. You're not supposed. If you were perfect already, then there's no point in being in this class, right? So I appreciate you sharing some of your difficulties, and I'll try to go through. I'll try to make sure that we address them in lecture today. My philosophy when it comes to computer science is, we're throwing you in the deep end of the pool. And we're gonna we want you to struggle a little bit, but we're not gonna let you drown. We want you to flail, because that's how you get stronger. But we're not gonna let anyone drown in here. So if anyone feels like they're drowning, let us know, okay? But we do want you to struggle a little bit. So allow yourself the opportunity to struggle, to sort of bang your head against the brick wall a little bit, and just keep trying. Don't give up. and I promise you'll get there and you'll improve as a coder as well. And don't get discouraged either. Like, this stuff is difficult. This stuff is really difficult. Don't think that you're not cut out just because you're having trouble with this. Computer science is notedly, and again, designed to be more difficult, which is why we save it for the end. The traditional way, like the way I learned it, is I learned computer science first in college, right? Like, we learned all these concepts like recursion and functions and object-oriented programming and things and data structures and algorithms. Like, I studied all of that before I wrote a single line of like production code to build a product. Like, I didn't do any of that until after college. So this is a very different way of learning coding. All right. Python 3. Got our graph class open. Yeah, it is probably more, I don't want to say it's just absolutely more difficult, but we are throwing more challenges at you. And I think in full stack web or in your main track, they're really pushing everyone along. So there's a lot more hand holding. And here again, we're sort of throwing you in and letting you struggle a little bit. We want to, one of the keys, I'll bring it up. Lambda School. One of our objectives with computer science is to build your confidence. And it seems counterintuitive that we're throwing really difficult problems at you to build your confidence. But the way you build confidence is not by solving easy problems, right? It's by overcoming difficult challenges. So that's so we're throwing difficult challenges at you, and then we want to help you. We want to help you overcome them and solve them. And then once you know that, our goal is that if you can make it through computer science, then nothing you encounter in your actual job will be difficult. This is going to be, Lambda School will be the hardest things you go through. So here's our mission statement for computer science. Let's see, quality. We want you to write quality code. We want you to write large quantities of code every day, building the reps needed to overcome difficult challenge and build confidence. So we want you to have to tackle difficult problems often. And we want you to struggle a little bit. We want you to, and then we want to get you to that aha moment. Aha! Oh, I get it. I get breadth first search now. And then because of the struggle, that's what's going to make it stick. If we just type out the code for you, if we say this is breadth first search and here's how to implement it and make sure you remember this, no way you're going to remember it. It's going to be the 3 hours that you spent. I don't get it. I don't get it. I don't get it. And then wait, I get it. I get it. And then you'll never forget it. Why did they decide to do all these challenges in a different language? A few reasons behind that. One is that if we did these in JavaScript, then all the full stack web people would have an advantage over the iOS people and Android people and machine learning people who come in who don't know JavaScript. Second is I think we went over this in Intro to Python, but second, which I touched on earlier, is that learning new languages is a very, very, very important skill to have as a coder. JavaScript and React may be hot right now, but what's gonna be hot in 5 years? Probably not JavaScript and React, right? That stuff will still be around, but it's not like the latest, hottest jobs are not going to be like that. I mean, that's just how the industry goes. Like, things are constantly changing. And as a programmer, if you want to have any longevity in your career, you need to be able to adapt and you need to be able to learn new languages. And the more languages you learn, like your first language may be JavaScript, and that was so difficult for you to learn. And you have your full stack web people kind of holding your hand, guiding you through there. Your second language will be Python, and we're still here to help you out, but we're not holding your hand nearly as much. And then maybe when you graduate, you find the perfect company, and it's the perfect match, but it's in Ruby on Rails. And now you have to learn Ruby, and now you're not going to have any of us instructors or anyone to help you through. All you're going to have is the internet and documentation. But since this is your third language, it's going to be pretty easy. You're going to find like, okay, how do I do a for loop? Okay, that's how I do a for loop. How do I get the length of an array? That's how I get the length of an array. It's all the same stuff. It's all just different syntax. So by the time you get to your third or your fourth or your fifth language, you'll find it gets easier and easier and easier. And then when you're applying for jobs, you can confidently say, like, no, I've never done C#, but I know how to learn. I can learn C#. You know, I already know 6 languages already. C# should be fine to pick up. So these are the reasons that we're learning Python. Also, Python in particular. So this goes back to, where is it? Readability. So Python, one of the key tenets of Python is readability. So if we look at, I don't know if Sean showed you this, but something I look at a lot is the Zen of Python. This is sort of the philosophy behind it. And they focus a lot on readability. So beautiful is better than ugly. What is beautiful code? There's a lot of components to writing beautiful code, but basically you want it to be short and concise and easily readable. And that's a really important skill to learn. And Python is sort of designed to be easily readable. So it's a really good language to practice. These are great questions though. Anytime you want, type import this, and you will see what Python is all about. Sparse is better than dense. Readability counts. These are really important concepts. Yeah, David, I think that we're well aware that you know, in 10 weeks, how much computer science can you learn? Like, I studied it in 4 years, and I still feel like, you know, I have not scratched the depths of all of CS. So how can we teach it to you in 10 weeks? Well, the answer is by going really fast. And you know, like we said, we're gonna let you struggle, but we're not gonna let you fit. We're not gonna let you drown. So if you had trouble with the graph class, I'm gonna go over it today, and you'll see. Okay, actually, it wasn't as hard as I thought. Like that's not bad. I'm going to go over breadth versus traversal, and you can see, okay, it's actually not as bad as I thought, right? But the struggles are key. The struggles are how you get stronger and how you get better. And that's what will make it stick in your mind. No more bokeh sprints either. So the sprint challenge will be changing. You're correct, Marshall. All right. Let's see. Let's get moving with this. All right, so we want to have a graph class. I'll come back to questions if Lambda isn't accelerating or helping your learning beyond a random series of YouTube videos. Well, hopefully, I mean, we have a PM structure. We have PMs to help you one-on-one if you need. We have, these lectures are live and dynamic, right? So if you're asking questions, I'm here to answer them. If you have trouble, yeah, at any time, if you have trouble, you can bring it up in the help channel. And, you know, I'm patrolling the help channels. I know the PMs are also patrolling the help channels. So I think that I would say that there's a lot more support than just random YouTube videos. You also have your peers that you're working with to help push you through and help know that you're not alone with your struggles. So I would say, I think that Lambda School is a lot better than just a series of YouTube videos. You know, I think, and, you know, we're putting a lot of thought into this, and we're constantly changing it, and we're constantly evolving it. So hopefully, you know, we're getting better, and we're listening too. We're listening to you all, and we're adjusting accordingly. So I think this is a lot better. But I mean, to your points, you know, if you want to learn about graphs, there's a ton of videos and a ton of tutorials about graphs. And if that's, if you want to look at that as supplementary material, like I totally encourage that. I think that, you know, I would say that we put a lot of thought into specifically Lambda students and how Lambda students learn. So I would say, even if it is just a video, that that it's more targeted towards you specifically. I mean, not you, but like at least your class and like the typical Lambda School student who comes into computer science knowing this much, you know, having 15 weeks of either full stack web or iOS or Android or machine learning, and and these are tailored to you, like this specific difficulty, right? If you look up like UC Berkeley has all their videos, or MIT or Stanford, they have a ton of videos on graphs, but those are targeted towards a freshman or sophomore college student who has gone through, you know, the MIT program or Stanford program. So maybe those aren't so applicable to you, but this is targeted exactly to you. Marshall, I don't think it's bad to study Bokeh. I think that it's a good, you know, that's not wasted time. One of the things that we liked about Bokeh is that it pushes you to learn a new library, which is something that commonly comes up in jobs. Like they're saying, we want to do some graph visualization. So, you know, implement this graph using Bokeh, and you're going to have to go in and read all the documentation and figure it out, and then come out with something. Right? They're not going to know if your assignment and your job is to do this. No, chances are no one in the company knows how to do it, and you're going to have to figure it out on your own. So that's a pretty common task. And we liked that it had you go through this, but there were a lot of problems with Bokeh. A lot of people had trouble getting installed. The documentation is not that great, so we felt that there was a lot of wasted time and frustration with Bokeh. That was not so frustration tied to like poor documentation is different from frustration tied to like, I'm trying to figure out this algorithm, you know. The latter we like. We want you to you know, stretch your brain and try to figure out these tricky algorithms. Trying to read through poor documentation, we don't think is as useful. So that's some of the impetus for the switch. Yeah, if you can get traversals working, search is the same basic thing. It's just there are some tricky things it requires you to really understand what's going on with the traversal in order to return the proper path. But it definitely builds on top of itself. Like if you can't do the traversal, then I think there's no chance you're going to be able to get the search right. And traversal is definitely simpler than just returning a path. All right, so let's get moving with this. We have a graph class, init a graph. Let's store, what does our graph class say? Graph says we want to implement a graph class that supports the API. All right, I guess I should remove draw.py. In particular, this means there should be a field vertices that contains a dictionary mapping vertex labels to edges. All right, sort of like this. So we can do this, self.vertices equals, we'll declare an empty dictionary, right? Let's implement our vertex class. Let's see, vertex. Let's see, class vertex. Def init self, always use self, pass in a vertex ID, and self.id equals vertex ID. I think that's it. I think that's all we have to do here. Now, what else do we need to do? So we need to create add vertex and add edge methods, all right? So these would go in our graph. Def add vertex, self, always use self, and then we want to pass in a vertex ID. So self.vertices of vertex ID should be vertex equals vertex ID. Okay, so do we see what we're doing here? Let's go over this. So first we're initializing an empty dictionary of vertices. And for this, we want our key to be a vertex ID. This is an edge list. We want the key to be a vertex ID, and we want the value to be a vertex. Was it necessary to use strings for the vertex label in the add vertex calls? String for the vertex labels and add vertex. It does not need to be a string because the key here is just any key, and in a dictionary you can have any type for the key. You can use an integer, and in some ways I think integer is better. But this should work. I mean, you shouldn't even have to change any code. You should just be able to do this. Note that if you're querying and you do a string 0, it will be separate from an integer 0. Did you have to implement the vertex as a class? It's simply a key. You don't have to, but this will come up later on as you fill out when you fill out your vertex class. We'll go over why more later, but it is useful to have a class for this. You implemented it as a key. So so you mean the key in the vertex dictionary? I mean, that could work. Let's do add edge, and then we can talk about this. Add edge. So to add an edge, self v1, v2. So we're adding, and these are gonna be like vertex IDs. Okay. So we can check if v1 in self.vertices and v2 in self.vertices. So this is checking if v1 and v2 both exist in your vertex list first. Then self.vertices v1 dot shoot, I think we should add edges to this. Self dot edges equals, make an empty set dot edges dot, I think it's add for a set dot add v2, and then we can do the same v2 v1. So this is adding a an undirected edge. We can do a method to add a directed edge later. Otherwise, else raise index error that vertex does not exist. How do you know you need a vertex class? One is graph, vertex, and edge classes. So I guess I would say that it says to implement this here, but I don't think you need an edge class, so maybe that's not a great instruction. Maybe the instructions are not that great. If you get this working without a vertex class, I think that's fine, but you may find yourself needing to add a vertex class later. Why don't I finish this up, and then other people who finished this and got it working can paste their solutions in Slack, and then we can go over them. Edges used a set, which seems to work okay. Yeah, so here's a set. So you're saying instead of adding a vertex, you just did like set something like this, and then you didn't have a vertex class at all? I think that would work, but it's nice to have a vertex class because then it lets you add stuff to it. Okay, so let's go through this, and then we'll come back and see directed edge. v1, v2 is the same, except we only add one edge. You just added edges set to the graph. Oh, so you added an edge list. You added a like self.edges here. I think that would also work. That's sort of what we talked about before, where you have an edge list. That's fine. That's fine. It's just I think that can also work, but this would be slightly more efficient to have your edge lists on your vertices. But I might be wrong. I might be wrong. You know, if I'll say this, if you're able to get all of your BFTs and DFTs and everything working, and you have an alternate representation, that's totally fine. It doesn't have to be exactly like this. This is just an implementation. What I will say is, I think as you go along, you might find cases where you would want a vertex class. Like for example, excuse me. If one way to tell if a vertex is visited or not, you can do like self.color equals white. And then when it's visited, you can do self.color equals black and change. And then you know the color.black means it's visited. And that way you don't have to look through your entire visited array, which is an N operation. So that's like one reason that you might want to have a vertex class. Can you explain why edges is defined as a set instead of a list? Sure. Let me see. Python time complexity. So I think this is it. Set. Where is a set? Set item. I don't think that's what this list is. A list. Here's a set. X in set. Okay. So if you're checking a list to see if something is in, it's an N operation. If you're checking a set, it's a big O of 1 operation. That's the short answer. So sets are better than lists. Sets, yeah, constant time. So to check if an item is in a set is constant time. Some restrictions on sets are that you cannot have a duplicate in a set. So if you have like 1 and 2 in your set and you try to add 1, then you're still just going to have 1 and 2. Another is that sets do not have any enforced order. So a set with 1 and 2 is equivalent to a set with 2 and 1. So if you don't care about order and if you do not allow duplicates, then a set is nice to use. Also, dir set. I don't know if you've learned the dir method, but I use it a lot. There's some different operations here, like is subset, is superset, things like that. Are you always expected to optimize going forward? If it's specified, you're expected to optimize, but if it's not, then you're not expected to optimize. Like for example, as you go, I added a here for your day 3-4 assignment. You're going to write an algorithm that lets you generate basically a random graph, and I want you to keep the runtime complexity to big O of n, which can be tricky, but if we specify it, then you're expected to do so. If not, then you're not expected. However, we may be going over this stuff in class. Like we may say like, all right, here's an implementation. How can we make it more efficient? But unless we specify, it's okay to do it however, as long as you create something that works. I thought doing list 1, 2, 3, 0 is big O of 1. No, that's not wrong, Brian. That's not wrong. If you're accessing an index that's constant time, however, if you are checking if something exists, like for example, if you wanted to say, does 3 exist in my list? That would be a big O of n operation. So like, let's see, 1, 2, 3, 4, 5. Here's a list. If you want to see 4 in, oops, let me make this L. L equals this. Then you want to see 4 in L. That's true. That's going to be a big O of n operation. 6 in L, false. But if we do it a set, S equals set 1, 2, 3, 4, 5. Okay, how do I do that? S equals set, S dot add 1, 2, 3, 4, 5. So here's our set. And if we do 4 in S, so this is going to be constant time. So that's the in operation. Yep, got it. You got it. All right. This is when, like, why do we study data structures? It's because sometimes using a different data structure can get you better performance. Like, for example, in this case, you want to use a set instead of a list. Because you know that you don't care about duplicates, you don't care about order. Hey, let's use a set. We're checking if something is in the set often. Like, it's worth it to use a set to get that constant time querying. So if you understand your data, and if you understand the use cases for it, then you can pick the best data structure for it. Do sets compare by value? That's a good question, and I do not know the answer, actually. I'm not sure how sets operate under the hood. You can look up the source code to see how it works. Okay, I don't want to open this. But the source code is written in C, so you may not know C yet, but by the time you finish Lambda school, you'll be able to read this C code. So that's a way to answer your question. Can you pull data from a set like a get? Yeah, you can. I don't know. Let's see. Dir sets. You can say intersection. You have all of these operations. So add, clear, copy, difference, update, discard, intersection. I don't think you can query by index. Like, you can't say get me the third index in the set, because sets don't have order. But you can see if something is in there, and then you can pop it out, I think. So, like, if we do s dot pop 3, okay, I guess you just, that's weird. Okay, it's weird that it pops it out in order, because that would imply that it does track order. So maybe sets do have order. Interesting. Let me see if I can do a help for this. Sets is a new set object. Yeah, look, this is weird. It says build an unordered collection of unique elements. But if you pop it, that seems to imply that there is an order, right? Because it pops it off in order. So that's interesting. That's very interesting. This, let's see, we added it 1, 2, 3, 4, 5, and we popped it in 1, 2, 3, 4, 5. So that would be like a queue, but I don't think it is like a queue. Is it enumerable? S.add. We're going off on a bit of a tangent here, but I think it's okay. 4, 5. So, okay, see, look, this is weird. So I added 1, 2, 3, 4, 5, but it popped up in this weird order. So what happened? What if we do 4 I and S, print I? Let's see what comes out. So it is enumerable, but it came out in a weird order, right? Because we added it 1, 2, 3, 4, 5, and then it came out 3, 2, 1, 4, 5. So I don't I don't exactly know what's how it gets the order, or what pop would be used for. But so if you cared about the order, then you would want to use a list or a stack, or I mean, I guess a queue if you wanted to come out in the order that you put it in. But it's not guaranteed. Yeah, David. So I know that sets are not supposed to be ordered, but that's why I wonder what's the function of pop. I guess pop just gives you a random, but it's not really random, right? It doesn't seem to be totally random. So what does help say? Help s.pop. Help says return and return. So pop just returns an arbitrary set element, but it's not really arbitrary. I guess it's arbitrary in the sense that you cannot guarantee that it's going to be any order. Yeah, Tom, that's a really great question. Data structures. So these data structures are good to look into. So I'm actually glad you asked this, because it gave us an opportunity to look deeper in. Why are we using this data structure? Well, for these reasons. We get better big O efficiency. We don't care about order. And we're not, we don't need to pop off in any order. So sets are very appropriate for this. And this is, if you're curious about the big O of various operations in Python, you can check out this. Yeah. All right. So as we were saying, I think as for the purposes of this, you could just do something like this. But for, I guess, looking into the future, I can see that it would be more useful to build a vertex class. But if you got everything running without a vertex class, that's perfectly fine as well. Just know that maybe you might want to add it later on. Like, for example, I didn't add an edge class, but I think I could. These directions could probably be more clear. So I'll update that for the future. Okay. So here is the basic code. Again, so adding an edge here versus adding a directed edge. So if you have an undirected graph, you want every edge to be bidirectional. So you do that by adding 2 edges. And if you're adding a directed edge, which only goes one way, then you only add 1. Okay, and then I'm also doing this check to make sure that the vertices exist. And if it doesn't, then I raise an error. All right, let's save this. It's status. I don't think I have a Git repository for this. All right. Next, let's do breadth first traversal. Def BFT. Actually, let's figure out. Let's see if we can draw this first. So subble graph demo. So this is a place where you can set up your graph using main. So you can do something like graph equals graph. It's a new graph. Graph dot add vertex. The difference between traversal and search is that a traversal, basically, of a graph, a traversal will visit each node. Search is if you're searching for a specific node. So let's see. So if we're doing a traversal from here, this is breadth first search. We'll do 1, 2, 3, 4, 5, 6, 7. We just touch every single one. If you're doing a search, let's say you're starting at 1 and you're searching for 6, you'll still do a breadth first. So you'll go 1, 2, 3, 4, 5, 6, and then you found 6. So you can just return true, which will say like, is 6 reachable from 1? That would be a breadth first search. Or you can return the path, which would say like from 1 to 6, you take 1, 2, 4, 6. Don't you need to traverse while doing a search? Yes, you do need to traverse while doing a search. It's more the difference is the return value. So also when you hit 6, you can stop. Whereas for a traversal, you're gonna walk through the entire graph. So that's why we do traversal first, because traversal is simpler. It's basically you run the breadth first algorithm, and you visit all of your nodes in breadth first order. Whereas search, you stop when you find something, and then you need to do some magic to get the path back. So let's add vertex 5. I made a thing like this. 5, 2. Maybe we can build this graph. All right, so we're gonna do 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Note that I'm not using strings here. I'm using integers. Then we will do graph dot add directed edge from 1 to 2. How many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have one from 2 to 3. From 2 to 4. From 3 to 5. From 4 to 6. From 4 to 7. From 5 to 3, from 6 to 3, what else? From 7 to 6, and from 7 to 1. All right, so here's our graph. We should we should be able to Python 3 graph demo.py. We run this, graph is not defined, so we need to import graph. From graph import. I think we can just import graph. Does this work? Or maybe we need to from graph import graph. All right, there we go. So we run this and it returns nothing, which is as expected. So now we can write our breadth first traversal. Now, when we last left off, I left you with a text version, def, bft, self, and then we need a starting node, right? Where is it? Where is it? BFT, self, starting node. All right, so what's our algorithm? Written out in words, it's create an empty queue, create an empty visited array, list, I guess we can call it, and then add the start nodes to the queue while the queue is not empty. So this is going to be a while loop, so I'm going to indent. While the queue is not empty, remove the first item node from the queue. If it hasn't been visited, mark it as visited, then put all its children in the queue. All right, so this is when we're talking about sentences. This is not quite pseudocode. This is an intermediate step between pseudocode. So you should be able to try to remember this. Okay, if you have trouble remembering how to implement breadth first search, breadth first traversal, remember this sentence. So create an empty queue, create an empty list to mark your visited nodes, and then add the start node to the queue. Okay, and then while the queue is not empty, pop the first node off, check if it's been visited, and if it's not, mark it as visited, then put all of its children in the back of the queue. Right? While we're doing this, I want to implement my own queue class, class queue, because Python's queues are a little bit weird. Def init self self.queue equals, we're going to use a list, def in queue self value, self.queue append value, def dq self no value, if self.size is greater than 0, that means we have stuff in our queue. Return self.queue.pop 0. That will pop the front of the queue off. Else, return none. And then last def size self, return len self.queue. All right, so here's our queue. Here's our queue. We can drop this in here and say like queue equals queue, queue.enqueue 1, 2, 3, queue.size gives us 3. Now we can queue.dq returns 1, 2, queue.size 1, and then we can dq. And if we dq and it's empty, it gives us none. All right, so here's a pretty simple Python queue. I just like this because I like to be, one, I can know what's going on under the hood. 2, it lets me name these just like how I like it. All right, so we're gonna use these. We're gonna use these here. Create an empty queue. So queue equals queue. Create an empty visited list. Yeah, exactly. Tom, you're exactly right. When we get to that, I'm gonna create a stack. empty visited list. So this is a list, but maybe we can make it a stack. I think we could make it visited equals, not a stack, a set. Why don't we make it a set? So I think that will give us some better performance. Add the start node to the queue, queue.enqueue, starting node, while the queue is not empty, while queue.size is greater than 0. Remove the first node from the queue. I want to indent these a little more. Remove the first node from the queue. Node equals queue.dequeue. If, let's see, if node not in visited, then visited dot add node, that's marked as visited, then put all of his children in the queue. All right, so that is for child in self.vertices. So self.vertices is the list of vertices. Nodes, I guess we can call this like node ID, but this is going to be the ID of the node. Dot edges. For each child, we can say if child not in visited, add visited dot add child. Okay, so let's mark it as visited. So this is interesting. Why we're checking if something is not in visited here, and then we're also checking it here. If we don't do this, if we don't do this check here, we're going to put visited nodes in our queue, and that's fine because we're just going to skip it here. Yeah, you could just add the child to the queue, and then it'll get skipped over here. So we could do that. Visited dot add child. Okay, a moment of truth. Let's see if we can run this. Oh, for visited, let's just print it out. So print node. All right, so this should print out our BFS. So let's run this again. Okay, I did nothing. Oh, here, graph dot BFT starting from node 1. All right, that does not seem right. Q.enqueue starting node, if node in visited, or child in self.vertices, node.edges. Am I missing something? All right, so we added all of these edges. We added edges from 1 to 2, from 2 to 3. All right, let's see if we can debug this. Print self.vertices.node.edges. Let's see what comes up here. So 1 is connected to 2. That's correct. 2 should be connected to 3. Why are we not putting its children into here? Print add child child. Let's see what comes out here. Add child 2. So we are. Oh, this is visited. This should be. It should be Q. Q.enqueue child. Hooray! I think this should work. All right, that looks better. Live coding is always exciting. Delete this, and run this again. All right, 1, 2, 3, 4, 5, 6, 7. Looks good. Looks like a valid breadth first traversal. So here's our graph. Again, we're starting from node 1, and we visit 1, 2, 3, 4, 5, 6, 7. It works out very nicely. What if we start from node 4? Let's see what will happen there. Start from node 4 and run this. We get 4, 6, 7, 3, 1, 5, 2. Let's trace through that. Okay, so we're starting from 4. We look at 4's children, 4, 6, 7. Then we look at the grandchildren. 6's child is 3. 7 is 6. The 6 is visited. And then we go to 1. Then we look at 3 and 1's children. That's 5. We get 5. Then we look at 1's child is 2. And then we go to 3 and 4, which have already been visited. So this looks like a valid breadth first traversal as well. Okay. All right. So that is breadth first traversal. Cameron, I think you caught my bug before I did. Okay. Any questions about this? About BFT? After the we're going to take a 5-minute break now. And then we're going to go into DFT, and then we're going to look at DFT using recursion. And then after that, we'll start talking about how to change these traversals into searches. Timer. And let's take a break. I'll put this this code here so you can look through it. All right, ladies and gentlemen, we are back. Okay, so I hope you got a fresh cup of coffee, and let's keep going. All right, so we have completed. We figured out how to do a breadth first traversal. We used a queue again. Even ignoring any code, just remember this. Create a queue, put your starting node in the queue, and then while the queue is not empty, pop off the first node. If that node has not been visited, mark it as visited, and then put all of its children in the back of the queue. All right, that's all you need to remember, and then you can probably muddle through the code yourself. So remember that. Create an empty queue, put the starting node in the queue. Then while the queue is not empty, dequeue the first element. If that element has not been visited, mark it as visited, then put all of its children in the back of the queue. All right. Now, a hint that I gave to you yesterday is that DFT, or depth first traversal, is exactly the same as BFT, except it uses a stack instead of a queue. All right, now for those of you who remember, can you tell me the order that items come off of a stack? LIFO, FILO, yep, same. Last in, first out, or first in, last out. So again, you think of that like a stack of pancakes, right? So first pancake, second pancake, third pancake, fourth pancake, and then you don't eat from the bottom, right? You pull them off the top, pull them off the top, pull them off the top, pull them off the top. So last in, first out. So since we're doing this, why don't we implement a stack while we're at it? Stack. Now, the traditional, so for queues, you have NQ and DQ. For stacks, you call them push and pop. So you push something on top of the stack and you pop it off the top of the stack. We'll call this push and call this pop. Stack.appends, and instead of popping off the back, we can just do pop here. And I think this should work. You can do it if you pull the bottom plate fast enough. Maybe. I've never actually tried that. I wouldn't recommend it if you like your pancakes. Whoa, that's not Python. This is Python. So let's test this out. S equals stack. S dot push. Let's S dot size 0. S dot push 1. Push 2. Push 3. S dot size. S dot pop. Pop off 3, 2, 1, none. Yeah, we should call this stack, not queue. All right, so we have our basic stack here. That's true. I guess what I actually do is I'll cut like a vertical slice and get like a four layer pancake. But I don't know if there's a data structure equivalent to that. All right, so we have DFT, and we can copy all of this over, except we change all instances of queue to stack. So why don't we, what if we just do a simple replace? So create an empty stack. Stack, S equals stack. Visited, let's make this still visited. S dot push, starting node. S dot size, well, stack is not empty. Remove the first node from the stack. Node equals S dot pop. If node not in visited, print node, visited add queue, blah, blah, blah. S dot push child. Okay, everything good. Am I missing any queues? Just here, stack. All right. Let's just give this a run. Let's see how this works. Start from 1 first. Python 3 graph demo.py. Okay, we got this return value. Let's walk through it. All right, so we're doing depth first search. I guess I haven't even talked about what depth first is. I guess we haven't even talked about what depth first is. Whoops. Okay, so why don't we first let's go over what depth first is. So this graph is slightly different from this graph, right? So ignore this, the code side for right now, and let's look at this. Will you get this code as reference later? Yeah, I'm okay with this. I'm okay with that. I think okay. So here's what I'll say about this. So I'm okay. I'm perfectly fine copying lecture code and giving it to you afterwards. I leave it up to the PMs to see if because I still want you to be working through this on your own. And if we see that students aren't doing their homework and they're just waiting to get solutions and then they're just copying the solution code, then I'm going to stop dropping code into. I'm going to stop giving code out. But I mean, for reference, I think it's fine. You know, you also have the videos. You can rewatch the lecture video and like pause it and get the code that way. So I think it's fine for you to have access to it personally. But you know, I know you're all adults, so just so make sure that you're not taking the code and not doing the work. All right, so let's look at depth first search. So again, depth first search is similar to breadth first search, except instead of going breadth wise, I guess this makes more sense in a tree. But instead of looking at all of your children, you take one child, and then that child looks at its child, and that child looks at its child, and then once you have no more children, then you go back up, and then you keep exploring. So like if we were to start from 1 here, we would go from 1. Whoops. We'd start from 1, 2, and then like let's explore our first child, which will be 3, and then we'll explore 3's child, which is 4, and then 4 hits 3. We've already visited that, so now we go back. 3 has no more children, so we go back to 2, and we explore 2's child, which is 5. 5 will look at its child, which is 6. 6 will look at its child, which is 3. That's already been visited, so we go back. 6 has no more children. We go to 5. 5 looks at its last child, which is 7. 6, which goes to 6, and 1. All right, so that's DFS. Let me see if I can. DFS graph. Let me see if I can Google this and come up with a better image. What's a good looking one? These are undirected, directed. These are all kind of ugly. Okay, these are not. Oh, here's a good one. Wikipedia, of course. Okay. So let's say we start from 1. What would be can people type out what a depth first ordering of these nodes would be? I guess actually looking at this, it's anyway. Yeah, Cameron, I agree with that. It would be nice to have more stretches. What I'm hoping, and sort of what the goal is with the added part. So if you're looking ahead to days 3 and 4. So this is a practical application of DFS and BFS. So at that point, so like when you get to days 3 and 4, I would be okay. Like I'm going to go through the solution lecture for DFS and BFS, right? So you will have that code, and then you'll be using that code to solve this bigger problem using the adventure game. So so it should build on top of each other, but we do still think it's important. We don't want to just hand you like BFS code on day 1, because I think it's important to solve it on your own. Whoa, okay, Anthony. So Anthony, you want to skip visited nodes. So I see that you're duplicating nodes. When you're doing a DFS, you should be ignoring duplicates. That's why you have your visited array, and then you skip over things that have already been visited. Yep, everyone is correct that it's just the numbers in order. So that's why I was thinking after I saw this, it's a little bit trivial. Can someone give me an alternate valid DFS route? So one where the numbers are not in order. Remember, these are stored as a set, so there's no actual order to them, right? So here we have 1 has children 2, 7, 8. Who's to say that 2 is the first child, 7 is the second, and 8 is the third, right? Like it's not like a binary search tree where you have the left and the right, and the left has to be less than the right. This is a graph, right? This is a general graph, so there's no ordering. When we have a set, we could get these in any order as well. Okay, so Linda has 1, 2, 6, 3, 4, 5. Yep. Then 7, 8, 12, 9, 10, 11. Looks good. Anthony has 1, 8, 9, 10, 11, 12, 7, 2, 3, 4, 5, 6. Awesome. Linda, Anthony, both great. All right. So how are people feeling? Maybe we put a poll. Polly, what is your confidence on DFS ordering? So this is make this 1 through 5. Make it anonymous. Submit to channel. Okay, so 1 is the less, 5 is the most. This is not having to do with code. It's basically if I gave you a graph like this, can you tell me what the DFS ordering is going to be? Or what is a valid DFS traversal order? So when we look at it this way, now when we look at a tree like this, it's easier to think of what it means depth first versus breadth first, right? Depth is like vertical and breadth is horizontal. So when we look at breadth, we go 1 layer at a time and we visit all of the horizontal and then we go a layer down and we visit all of this breadth and we go down and we visit all of this breadth. So that's why we visit 1 first, and if we're doing a breadth first search, we would visit all of his children, so 2, 7, 8. Then we would do all of the grandchildren, which are 3, 6, 9, 12. Then we go to the great-grandchildren, which is 4, 5, 10, and 11. Now, when we're doing depth first, you see we go deep. So we trace 1 lineage until we're all the way to the end. So we go 1, 2, 3, 4. Can I make this bigger? So we go 1, 2, 3, 4. And then we hit 5 here. And then we go back up and we visit 6, 7, 8, 9, 10, 11, 12. Okay, so we have a kind of a bell curve. So we have a lot of 3s and a lot of 5s. We only have 16 votes. Okay, some people are not voting. We have 42 people in this room, and I know that there are not 26 PMs. So everyone put up your confidences here. Unless maybe 20 people are asleep. Okay, we have a 1. It might, if you fork it, it may not get the update. Maybe, I don't know. Yeah, I'm sorry about the chaos, but either you can refer to the web version, or you can clone it, or you can download a new version and then just copy over your README to the new one. Okay. Okay, so whoever is the 1, I think maybe if you ask your PM for help, that could be a good idea. For those of you who are 3, so there's a good amount of you who are 3, and enough where maybe we should What's a good way to do this? Maybe it'll help to look at the code. It might help. So one way to look at it is to think of this tree, is to think of it as a tree like this. And any graph can be put into a tree like this. When you're looking at your graph like this, it's not really that clear where your starting node is, but you can put, like if you're starting from 1, you can put the 1 at top and then the 2 and 3 down, and then you can look at the children that way. But this is an easier way to visualize like what depth first means versus breadth first. Cool. Python tutor might help. I haven't used Python tutor for Python, but I use it a lot for C. But I really like that tool. So that could, I definitely recommend using Python tutor if it helps. Okay, so again, so for depth first, for breadth first, you look at the children, grandchildren, great-grandchildren. For depth first, you trace one line all the way down, and then you keep, once you have no children, then you go back up to your parents, and then you look at all of its children, and once you have no more children, you go back up the stack. I think when we get to recursive, when we actually look at the recursive depth first search, it might even make more sense. Okay, so let's jump into some code here. All right, we did our DFT. Do we run it? This, yes. And we got this 1, 2, 4, 7, 6, 5, 7, 6, 3, 5. So we have 1. We look at 2. We look at 2's child, which is 4. Okay. And then we look at 4's next child, which is 7. And then 7, we look at 1, but 1 has already been visited, so we skip that. We look at its next child, which is 6. So again, one note is that even though we have 4, 7, 6, this is looking at 4, and then 7's child. 4's child is 7, and then 7's child is 6, right? So we're hitting this 6 via 7, not via 4. So we're hitting 4, 7, 6. When we're at 6, we look at 3's. We look at its child, which is 3. 3 looks at 5. 5 looks at its child, which is 3, has been visited before, and has no more children, so we go back up. 3 has no more children, so we go back to 6. 6 has no more children, so we go back to 7. 7 has no more children, so we go to 4. 4, we haven't even looked at 6 yet, right? Because we went straight to 7. So 4 will look at 6, and then we've already visited 6, so we skip it. And that's our entire DFS using a stack. We can, why don't we walk through this? Why don't we walk through this the same way we did the other one, using a list. Would this come out the exact same way if you ran it 100 times? Yes, it would come out the same way. But I guess it depends on the stack implementation. So since we're using a list as a stack, it should come out the exact same every time. But yeah, it should come out every time. It should come out the same every time. We could do something like we could shuffle the edges. So that would be interesting. How do we do that? For child and self.vertices shuffle, we could like shuffle this. Let's see. No, edges is going to be a set, so I don't know how to shuffle a set. But it depends on the order that it gets put in from your edges. So I guess depending on the Python implementation, the order that you get the children from the edges list, the edges set, will determine the order that it comes out. But that's not. But this is not the only. This is not the only valid. The only valid way to do it. Is NQ and DQ doing the same as push and pop? Yes, it's just for a queue versus for a stack. So stacks use push and pop, and queues use NQ and DQ. Just to be explicit about it. All right. I want to walk through this because I think this is a pretty good example. So we have our stack. Let's make an empty stack. Visited, make an empty list. And let's look at this thing. 2, 3, 5. It is valid. So why don't we do it that way? Why don't we look at it that way? So stack, we create an empty stack. We created an empty visited array. Just call it visit, so it's the same length. And we push the starting node on top of the stack. So our starting node is going to be 1, right? While size of the stack is greater than 0, we pop off the top of the stack. If it hasn't been visited, we mark it as visited, so we put it here, and then we put each of the children onto the top of the stack. So this is where we can get randomness, right? Oh, I guess we only have 1 child, so we have 2. Pop off 2. Hasn't been visited, so we put it on our visited array. Now we look at 2's children. Now 2 has 2 children, right? 2 has 3, and 2 has 4. So we can either put like this, or we can do it for 3. And both of those are totally valid. Let's say we want to hit 3 first. So last time we visited 4 first, right? So what if we visited 3 first? So that'll be like this. So now 3 is on the top of our stack. Top is on the right. Okay, so now we pop off 3. 3 hasn't been visited, so we put it here, and we put all of 3's children onto the stack, which will be 5. 5, now we pop off 5. 5 has not been visited, so we put it here, and then we look at 5's children, which will be 3. So we can put 3 here. If we do the visited check here, then we wouldn't put 3, but we could put 3 here anyway, since we're doing a visited check anyway. All right, so anyway, we go to the next, we pop off 3, we see 3 has been visited, so we ignore it. All right, next we pop 4 off the stack. 4 off the stack has not been visited, so we put 4, and then we put 4's children. Now 4 has 2 children, 4 has 6 and 7, so we can either do 6, 7, or we can do 7, 6. And that'll determine the order that we get returned from our DFT. So let's do this way, 6, 7. All right. Now we pop 7 off the stack. We pop 7 off, and we put 7's children onto our stack. 7 has not been visited, so we put that here, and we put 7's children. Now 7 has 1, and 7 has 6. 1 and 6, right? All right, so now we pop off 6. 6 has not been visited, so we put that here. And then we look at 6 children. 6 has 1 child, which is 3, so let's put 3 here. Next, we pop off 3, and we check if 3 has been visited, so we skip it. We look at 1, we pop off 1. 1 has been visited, and we skip it. And then we pop off 6. 6 has also been visited, and we have an empty stack, and we are done. So this gives us 1, 2, 3, 5, 4, 7, 6. 1, 2, 3, 5, 4, 7, 6. Perfectly valid DFT. Any questions? Any questions about what we just went over? So for me, I think this is pretty mind-blowing. This is like a mind-blowing thing where when I realized all you have to do is change your data structure from a queue to a stack, and you go from BFT to DFT. Like what? I think that's kind of amazing. I wish I had like an elegant way to describe it. Well, like because vertical stack, I guess you can think of as vertical, like a stack of pancakes versus a queue grows horizontally. So that's sort of like breadth first versus depth first. But I still feel like there's something I'm missing why that works. But it does work. It does work, which is just really cool. Good question. How does BFT and DFT compare? When is one better than the other? That's a really good question. So DFT is usually used if you think of like a maze. Like let's say you're trying to get from one end to the other, and you're using a maze. You usually how do you usually solve a maze, right? Like you'll draw a line, and then you'll go all the way until you hit a wall, and then you'll backtrack until you get to another intersection, and then go down another path, right, until you hit a wall. So that's what DFT is doing. That's like DFT, right? You don't draw like a line, 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 line. Okay, then draw another line, another line, another line, another line, another line. You know, you don't radiate outwards. You draw like a line until you hit a dead end, and then you backtrack. So that's DFT. Like if you're solving a maze, you can use DFT. Something like Google Maps will, if you do DFT with Google Maps, like you're trying to get from here to here, you may end up going down this long, crazy line and end up, you know, in North Dakota when you're just trying to get down the street to their store. So in that case, you would want to use breadth first search, right? Where you basically grow outwards until you reach that. BFT is guaranteed to give you the shortest path, whereas DFT is not guaranteed to give you the shortest path. So Google Maps also does some optimizations. For example, like if you're trying to get to the store here, it probably doesn't check paths this way. So that's easy if you want to look up Dijkstra's algorithm, and Dijkstra has a very difficult spelling. It's D-J-I-K. Okay, I spelled it wrong already. Dijkstra's algorithm. Dijkstra's algorithm. So this is this is sort of using breadth first, but it uses optimizations, and it takes into account weights. And if you want to look even further, you can look up A star search, which takes in weights, and it uses what's called a heuristic. So that's saying like it will make an estimate. If you're going from here to here, you're probably going to want to check these paths first, basically. So why does BFS guarantee the shortest path? Okay, good question. So if you're starting from, let's say, all right, let's think of Google Maps. All right, let's say you're starting from like your house, right? Basically, what BFS does is it says, all right, let's take one step north, south, east, west, right? So one step here, one step here, one step here, one step here. Have we hit our destination? No. Okay, let's try 2 steps. So 2 steps here, 2 steps here, 2 steps here, 2 steps here. No? Okay, let's do 3 steps. Okay, now we have a branch, so we'll do 1, 2, 1 step here, and 1 step here, then 3 steps, 3 steps, 3 steps. All right, so that's what breadth first search is doing. And then, like, let's say the store is 10 steps away, so you get to 10. You've gone over all the possibilities that you can get with 1 step, 2 steps, 3 steps, all the way up to 9 steps, and you were not able to find the store. Then you try 10, and then you get to the store on the 10th step. So you're guaranteed that there's no way to get to the store for any combination 9 and below. Yeah, graph problems come up a lot in coding interviews for a couple of reasons. One is that graphs are really useful. Like Facebook, for example, if you're applying to some place like Facebook, their entire social network is called the social graph, and they have an API called the Graph API. So they do a lot of graph traversals. Things like Google, all of their stuff is a graph. You know, cloud computing, it's all one big graph. So graphs are used everywhere. HTML, if you're looking at HTML, HTML is basically one big graph where, you know, if you have a P inside of a div, that could be like a div that's pointing to a P. So it can be reduced to a graph format. And traversals are used all the time. Another reason that graph questions come up a lot in coding interviews is because they're actually pretty short. Like if you know what you're doing, it's not a lot of code, right? Like you can, like this entire DFT is like minus comments, like less than 10 lines of code. So if you know what you're doing, you should easily be able to write solve a graph problem within like a 45-minute interview. So so you're correct that graph problems come up a lot. So, sorry if you're can you see my hands? Am I sometimes I'm just gesturing like a maniac, and I realize that may not be the best for Zoom. Okay. Oh, okay. Oh, you're missing out on my pantomime, on my graph dance, my interpretive graph dancing. Okay. So where were we? We created a DFT using a stack and a BFT using a stack. All right. We have one more issue that I'm going to let you go through, let you try to go through on your own. That's DFT recursive. All right, now you've all studied recursion, right? Let me put up a poll here. Confidence with recursion. And let's make this 1 through 5 and anonymous. Submit. All right, 1 is the least, 5 is the most. Just the concept of recursion. Okay, recursion is tricky. Recursion is tricky. And the reason it's tricky is because it's actually extremely simple. Like when you write a recursive function, you can, it's very little code. It's very, very, very little code, and you can do some pretty complicated stuff with that. So for example, if you do depth first search using recursion, you can write it in about 3 lines of code. So how much do we do here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines of code. If you do depth first traversal using recursion, you can do it, I think, in about 3 or 4 codes. Yep, Cameron, you got it. So basically, if we're writing it out in the sentence, all right, this is a sort of what I expect. We have a nice bell curve here, sort of centering on 3, a little bit leaning towards the unconfident side, but this seems pretty good. So recursion, to refresh your memory, is basically you have a function that calls itself. If you want like a simple, like factorial, for example, a very simple recursive problem is the factorial function. So factorial, again, if you don't remember from high school math, will be like factorial of 10 is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So if you wanted to like define factorial of n, you could do a few things. Like you can do it iteratively. So like f equals 1, then for f for I in range 1 to n, f times equals I earn f. I think this should work. Factorial, let's do 5. So that's not right. 5 plus 1, n plus 1, is that right? All right, that's better. Okay, so factorial, so you could do it this way, which basically goes through every number and it multiplies it by itself. Or you can do it recursively, which would be if n is greater than 0, return factorial. I guess this isn't that much, that many lines less code, but you can do return n times factorial of n minus 1, else return 1. I think this should also work. Yep. Okay, so you see what we're doing here? This is an iterative approach where we go through each item and we do something with it. This is a recursive approach where we call the function itself. So this is going to be a recursive approach. You can notice that because we have this iterator, which is a while function. So while s.size equals 0, basically we're iterating through a bunch of different things. Whereas recursively, we have no while loop. We just keep doing this until we hit what's called the base case, which is when the recursion stops. Yeah, you can do this stuff. You can do this stuff in like 1 line of code using ternary operators. So something like, will this work? N greater than 0, return Does this work? I don't know if this is how to do ternary in Python. Okay, it doesn't work. But this ternary operator works in JavaScript. Is this how you do it in JavaScript? I don't remember how to do it in Python. But you could reduce it down to one line using some things like this. I don't remember if Python has ternary. It probably does, but it's probably some different syntax. So this is also sort of what I mean, where learning languages build upon each other. Because now you can look up like Python ternary. Does Python have ternary conditional operator? Blah, blah, blah. A if, okay, so let's try that. A if and else. All right, factorial 5. 120. All right, so this does work. So we got it down to one line of code. It is verbose, but again, this is pretty close to English, right? Like do this, if this, else do this. Which is like close. This is basically pseudocode, right? This is very, very, very close to pseudocode. Whereas if you're using the question mark colon ternary operator, it's a little that's a little more foreign to English, right? But anyway, so this is a recursion example. We can do a similar operation with DFS or DFT, right, to be specific, using where's our picture? Here we go. Okay, so basically, here's what our sentence is going to look like. I need to delete this. So def DFT R for recursive, self starting node. All right, so here's what we do. Mark node starting node as visited, then call DFS R on each child. And that's it. That's it. Wrap your head around this. Mark the starting node as visited, then call let's call this DFT. Then call DFT recursive on each child. All right, think of that. Mark starting node is visited, then call DFT recursive on each child. That's it. 2 lines of code. You can traverse through a humongous graph using only these 2 lines. So how does that work? All right, let's walk through this. Mark the starting node is visited, then we call DFT on each child. So let's start with 1. So we mark 1 is visited, and then we go to 2. We mark 2 as visited, and then we call DFT on each of his children. So that will give us 3. All right, so this is an important transition. So we start from 1, we call DFT on its child, which is 2, and then what is DFT? Mark this as visited, then call DFT on each child, right? So why do we go to 3? Why do we not hit 7 yet? Well, it's because 2 hasn't finished running DFT. So DFT finishes when you have no more children left. So 2 still has children. So 2 needs to call DFT on its children. So it'll call DFT on 3, right? Oh, let's call it on 6. Let's call it on 6 first. So 2 called DFT on 6, right? So mark 6 is visited, then call DFT on each child. 6 has no children, so it's done. So this DFT recursive returns. So we return here. So now 2 has called DFT on 6. Now 2 needs to call DFT on its other child, which is 3. So we call DFT on 3. Mark 3 as visited, then call DFT recursive on each child. So 3's first child is 4. Mark 4 is visited, then call DFT on each of 4's children. 4 has no children, so 4 returns, and we get here. Now 3 has finished calling DFT on 4. Now 3 needs to call DFT on 5. So he calls DFT on 5, mark 5 is visited, and then 5 calls DFT on each of its children, has no children, so it returns. Now 3 has finished calling DFT on each child, so it returns to 2. Now 2 has finished calling DFT on each of its children, so it returns to 1. And then all 1 knows that DFT has been called on 2, okay? Now it needs to call, that's one of its children. Now it needs to call DFT on the rest of its children. So it calls DFT on 7. So mark 7 is visited, then call DFT on each of its children, has no children. So 7 is done, it returns. And we go to 1. 1 has now called DFT on 2 and 7, so it calls a DFT on its last child, which is 8. 8 calls DFT on 9, mark 9 is visited, call DFT on 10, mark 10 is visited, no children, so 10 returns, call DFT on 11, 11 has no children, so 11 returns, 9 has now called DFT on both of its children, so it returns to 8. Now 8 has only called DFT on 9, so now it calls DFT on 12. 12 has no children, so it returns. Now 8 has finished calling DFT on each of its children, and it returns to 1. And 1 has now finished calling DFT on each of its children, so now 1 is done. Phew. Okay, so that's a lot. So as you can see, even though this code is only 2 lines long, or 2 sentences, if you will, even though there's only 2 steps to DFT recursive, you can built into that too, you can traverse through this entire graph using depth first traversal using only those 2 lines. So again, mark the starting node as visited, then call DFT on each of the children. That's all you have to remember. Even easier than remembering this. Does that make sense? All right, I'm gonna leave the recursive solution for you to try to solve in your homework. But remember these sentences, okay? Are there any questions about this recursive method of DFT? Do you have to start at the root node, or can you start anywhere, like at 4? You can start anywhere. You can start anywhere. Let's see. If this is a directed graph, which it doesn't look like a directed graph because there's no arrows. If it's a directed graph and like 3 is pointing to 4, then 4 has no children. But if it's an undirected graph, then you can go from 4 to 3, 5 to 6, and so on. And that should work just fine. Roots in a graph, in a tree, there's always a root node because trees start from a root. Graphs can have no root. Like a graph can be like 1, 2, 3, just in a triangle. I think there's an example of that here. Graphs intro. So like this is a graph, right? There's no root node. You can start anywhere, and it's perfectly valid. But you can do DFT through this also because you just look at the children, right? So if you're starting here, DFT will go to this child, mark it as visited, visit its child, mark this as visited, go to here, it's been visited already, so then we go back up, and it'll work the same from wherever you start. If the graph is bidirectional, do you need to do anything else in the graph class or vertex class or edge class? You shouldn't need to. You shouldn't need to. Here is going to be the distinction. Okay, where's my graph? Where's my graph? Here we go. Okay, so Cameron, imagine that so this is a directed graph, but imagine that each of these is bidirectional, right? So 1 points to 2, 2 also points to 1. 2 points to 3, 3 also points to 2, and so on. All right, so we're going to look at 1's child, right? 1 has 1 child, or I guess it has 2 children, which will be 2 and 7. So we visit 2 first, and then we mark it as visited. Let's say we're doing depth first. Okay, so we visit 2, we mark 2 as visited, and we look at each of 2's children. Now 2 has a child 3, 4, but it also has 1. So 1 will also be a child because it's pointing to the 1, right? But 1 has been marked as visited already. Since we visited, we started at 1, it's been marked as visited. So once we check for 2's child, 1 is just going to be ignored. So we skip it over. So if you have a bidirectional graph, it should you may have a lot more visited checks, but it should function exactly the same. Good question though. All right. So now we've gone over breadth first traversal, depth first traversal, and then we've looked at how do you do depth first traversal using recursion. All right, now this is the trickier part. Is we know how to walk through an entire graph. It's not too difficult. It's not too difficult to transition into search. So let's start with search. We'll copy all of this. So breadth first search, starting node, destination node. So this is going to be very similar, except we have a destination node. So basically, we want to see, do we get to search, general search will just say, like, can we reach this node from our starting node? So we can return true or false. The more difficult is to, once you get the destination node, to figure out the path from the starting node to the destination node. Okay, so I'll walk through how to get to, how to find the destination node, just returning a Boolean, like a true or false. And I'll leave it up to you as an exercise to return a path. Okay, so BFS, we can start the same. We'll do, this is all the same at the beginning. If node not in visited. Okay, so here when it's visited, this is when we're doing a check, right? Like, you may think, what does it mean to mark as visited? This could be any number of things. This could be like changing the color of your node. It could be, if you're searching for a specific node, it could be like, all right, this is when we look at it and do our check. All right, so let's see if we can do that here. We can say if destination node equals node. Whoops, don't need that. Then return true. Visited. Otherwise, if we get to the end, return false. Okay, I think this is all we need. Does that work? Is that it? Maybe I'm missing something. Well, let's try it. DFS. So if we should be able to hit all of them. So if we do like 5, we should just get true. Python 3, graph demo. Okay, indentation error. Pass. Graph has no BFS. Good catch, Michelle. Okay, we did not. Oh, we should print this out. Print's true. Okay. True. Let's see if we can generate a false. What if we create a vertex that's 8? And let's see if we can find 8. So this has no edges. So this is a lonely 8 hanging out there. So we should get false here. False. Okay. Nice. Let's see if we can make a more interesting example. So what if we All right, what if we remove this 7? So what if we remove this 7 to 1 edge? And then we start from 2. And we'll look for 1. Okay, so we removed this edge here, this 7 to 1 edge. We're starting from 2. Now this 1 is still connected to our graph, right? But we shouldn't be able to reach it through a DFS. So let's see what we got here. False. Cool. Well, what if we made this an undirected edge? So 2 to 1. We'll make this an undirected edge. This should give us true. True. Okay. What is the result if you're looking for a path? Good question. If you're looking for the path, let's see. So if you're looking for the path from like 2 to 6, let's say, you should return like 2, 4, 6. Maybe like an array, like 2, 4, 6. This would be a path. Note that there will be, like, if you're going from 2 to 6, you could also do 2, 4, 7, 6. And this is also a valid DFS. Like if you're going from 2 to 3, you might get something like this. 2, 4, 7, 6, 3 for depth first. And that's a perfectly valid depth first path. If you're doing breadth first, it will always give you 2, 3. Because breadth first is guaranteed to give you a shortest path. Right? Okay. Any questions? Any questions about this? About just returning true and false? Okay, now the tricky part, and believe me when I say it's tricky, is that you're going to need to track the path. Okay, so how do we track the path? Well, one way to do it is what are we putting in the back of our queue? We're putting children, right? So we have visited equals blank, queue equals blank. What's our basic thing? For breadth first, we put 1 in the queue. We put 1 in the queue. 1 here. We pop off 1. We put it here. And then we put all of its children in here. So that will be 2, right? 2 we pop off. We put it here. And then we have its children. 3, 4. Okay, so that's all well and good. But how do we get the path from this? Well, one way you can do it is when you put stuff in the queue. Is that you queue up a path instead of this. So what do I mean by that? So we start with 1 in the queue. Instead of 1, we put a list 1. All right, we dequeue this. And I think we can just put 1 here. And then we put each of its children here. So we know that 1, we know that 2 is the child of 1, right? So we already know 1 exists here. And then we can put 2 here. Okay. And now we dequeue. We know that the node we're looking at is going to be the last element in our list, right? So now we dequeue 2. We check if 2 is visited, so we put 2 here. And then we put each of 2's children in the back of the queue. So we already had 1, 2, right? So we put 1, 2, 3 here. And then 1, 2, 4, 4. All right, now here's our queue. Now we pop off 3, and the node we're looking at is 3. So we pop off this. We'll store this here. So we know we have 1, 2, 3. We're looking through our last node is going to be the node we're looking at. So we put visited in 3. And then we append each of its children. So 3's children are 5. So we put 1, 2, 3, 5 in the back of our queue. Now we look at 1, 2, 4. We pop this off of our queue. We're looking at 4, node 4. So we would put 4 in our visited queue, and we put 4's children in our visited. We put 4 in our children. So that's 1, 2, 4. And what's 4's children? 6, 6, and then 1, 2, 4, 7. All right. So do you see what we're doing here? In our queue, we are storing not only we're not only storing the node that we're looking at, we're storing the node and the entire path to that node. And then when we're checking the node, if it's visited, we look at the last elements in our queue, in our path, and we check if that's visited. So is 5 visited? We look here. And this also when we're doing this check, right? We want to see, all right, are we looking for 5? Are we looking for 5? If we are looking for 5 with our BFS, then we can add 5. Then we know we've returned, and then we return 1, 2, 3, 5. If we're looking for 6, we have our path that we can return here. 1, 2, 4, 6. If we're looking for 7, we can do 1, 2, 4, 7. And again, since this is breadth first search, we are guaranteed that these are all going to be the shortest possible path. Now, it's not the only path. It's not the only path necessarily. For example, let's see. Let's say that this arrow from 3 to 6 pointed the other way. So 3 points to 6. The shortest path from 2 to 6 would be 1, 2, 4, 6, but you can also go 1, 2, 3, 6. And you would only get one of those. And those paths would be the same length, so you're not guaranteed which one you're going to get first, but you know that it's going to be the shortest path. It's not necessarily the shortest when you get to depth first. So for example, if we're looking for 3 in depth first, you might go 1, 2, 4, 7, 6, 3. And that's obviously not the shortest path. The shortest path would be 1, 2, 3. So that's a really important distinction. If you want the shortest path, you can use breadth first search. Okay, that is okay. So we're out of time, but I think we got through most of it. Implement breadth. So we went over 1, 2, 3 today. Well, we didn't go over 3. Oh, we did go over 3. So we went over 1, 2, 3 in lecture. For homework, implement depth first traversal using recursion. Implement breadth first search, returning a path, and implement depth first search that returns a path. I recommend while you're working on BFS and DFS, that search, that you start with just this true and false. And once you get that working, try returning the paths. Awesome. I'm glad you're enjoying it. Okay, cool. And I am okay to drop this code in for you. Don't abuse it. If you don't get it, try to work through this stuff on your own. But yeah, good luck, enjoy, ask questions, drop them in the help channel, and we'll be around. All right, thanks everyone.